Section 1.4, Equations of Lines. In this section, we have several objectives. We'll look at writing equations of lines using the slope-intercept form as well as the point-slope form. We'll write equations of horizontal and vertical lines. We'll look at parallel and perpendicular lines and how to write those equations. We'll look at the average rate of change for non-linear functions over a specified interval of inputs. We'll also look at finding the slope of a secant line between 2 points on a graph and finding the average rate of change for approximately linear data. All right, in the last section, we were talking about the slope-intercept form for the equation of the line, y equal mx plus b. We'll expand on that a little bit when we're thinking about the graph of the equation of a line. M is the slope of that line. In context of an application, though, that slope is considered the rate of change for that line. The graph of a line in the form y equal mx plus b, the b is the y-intercept, or where that line intercepts the vertical axis. In the context of an application, b in this form for the equation of a line can be considered the initial value. Oops. All right, let's look at an application. Say a plumber charges $65 for a service call plus $30 per hour for each hour spent on the repair. All right, assuming his service call charges can be modeled by a linear function of the number of hours spent of the repair, write the equation for the function. Well, if we use this slope-intercept form, right, we know that the m is going to be the rate of change and the b is going to be the initial value. All right, so looking in the context of this application here, what would be the rate of change? Well, it looks like the thing that's changing is the per hour charge, right? So $30 is going to be our rate of change, $30 per hour. Whenever we see per, you know, that's a rate of change. Like when you think about when you're driving your car, if you're driving at 35 miles per hour, your speed or your rate of change in the distance your car travels is the speed, the 35 miles per hour. All right, and then so we can say y equals 30x, and then what would the initial value be? Well, for the charges this plumber is giving, there's $65 that he will charge or she will charge, you know, regardless of whether any work is done. So that's going to be the initial value of the cost of this visit. Y equal 30x plus 65 would be the model that could be used to determine the charges this plumber would charge you. All right, there's another form for the equation of a line called the point-slope form for the equation of a line. And this is helpful. This is helpful when we know a point on the line, but not necessarily the y-intercept, right? This form says y minus y1 equals m times x minus x1, where this y1 and this x1 are the x and y coordinates of a point that is on that line, or an ordered pair that satisfies the equation of that line. M, of course, is your slope. So let's look at an example of writing an equation of a line in the point-slope form. All right, so our format, y minus y1 equals m times x minus x1. All right, and we want to write this equation for a line that passes through the point that has the coordinates -4, 6. So our x1 is -4, our y1 is 6. And we know that the slope is 1/4, so that's our m. All right, so plugging these values into this format, we'll have y minus, see, y1 is 6, is equal to m, that's the slope of 1/4, times x minus, and our x1 is -4. So it'd be x minus -4. Right, if we simplify, we have y minus 6 equal to 1/4. And then x minus a -4, of course, is x plus 4. And there's our point slope form. However, this isn't very useful as a model. The more useful format for the equation of a line, if we're modeling and we're using it to predict or estimate values, we would want it to be in the slope-intercept form. So to do that, excuse me. So to have the slope-intercept form, we simply have to solve for y. All right, so our first step would be to distribute that 1/4. So we'll say y minus 6 is equal to 1/4 x, and then plus 4 times 1/4, which is just 1. Okay, then we'll add that 6 to both sides, and we'll have y equal to 1/4 x plus 7. Okay, now that we have this in the slope-intercept form, y equal mx plus b, we can see that 7 is our initial value. On the graph, this, of course, is going to be the y-intercept, or the intercept to the vertical axis. All right, let's look at an example in context. Here's some data that shows blood alcohol content, percentage of blood, the percentage of blood the blood alcohol percent, there we go, for a 180-pound man, for 3 drinks consumed, 4, 5, 6, so on and so forth. All right, part A says, is the rate of change of the blood alcohol percent constant? If it's not constant, then we don't have a linear function. So let's see if it's constant. Well, the blood alcohol percent is the y, and the rate of change looks like when we go from 3 to 4 drinks consumed, the blood alcohol percent goes from 0.07 to 0.09. So the difference there is 0.09 minus 0.07, or 0.02%. All right. If we continue on, we look at the difference from 4 to 5 drinks. Well, that's also 0.02%. From 5 to 6, 6 to 7, so on and so forth. All of them increase by 0.02%. So we can say that there is a constant rate of change here, and the rate of change is 0.02. If that is constant, and we know this is going to be a linear model, all right, and that 0.02 is going to be our m in that model. All right, now what is it? Let's see, it's 0.02. Answer part A. Part B, write the equation of the function that models the blood alcohol percent as a function of, it's as a function of the number of drinks, right? So blood alcohol percent would be the y, because it's a function of the number of drinks. The number of drinks would be our x. Okay, so to write this equation, let's use the point slope form, because we know the slope because we just found it. The rate of change is 0.02, and we have several points that are on that line, or several points that satisfy the equation of the line, right? So we'll use the y minus y1 equals m times x minus x1, or the point slope format for the equation of a line. All right, so plugging in the coordinates of a point with the slope. Let's see, we'll just use this first point. We'll use these coordinates here, right? So we're going to plug the 0.7 in for the y1, and we'll plug the 3 in for the x. And we did just find our slope to be 0.02. So then we have y minus, let's see, 0.07 is equal to 0.02 times x minus, and that would be 3 drinks, so x minus 3. Okay, so there's our point slope form. Again, it's not very valuable as a model. We'll probably want to solve for y here. So we have a model in slope-intercept form that tells us our rate of change and our initial value. Okay, to solve for y, we'll distribute that 0.02, and we'll have y minus 0.07 is equal to 0.02x minus 0.02 times 3, that's 0.06. Okay, we're out of room, so we'll go over here. Then we'll just add that 0.07 to both sides. And we'll have y is equal to 0.02x plus 0.01. And there we have a model that we can use to determine blood alcohol percentage based on the number of drinks consumed for a 180-pound man. All right, let's look at another example. This one, we aren't told what the rate of change is or what the slope is, but we do know that the equation of this line, if graphed, would pass through 2 points. We also know the coordinates, 2 sets of coordinates that satisfy the equation of the line or make it true. The first point has an x coordinate of -2 and a y coordinate of 3. Second point has an x coordinate of 4 and a y coordinate of 7. So we'll call that one y2, x2 and y2. Okay, so using our point slope form, we have y minus y1 equal to m times x minus x1. We can't simply plug in and use this though, because look, we don't know what the slope is yet. We've got to find that slope first. We don't know what it is. All right, we do know how to find the slope, right? We have an equation for that. It's y2 minus y1 over x2 minus x1. Difference in the y's over the difference in the x's, or rise over run. All right, and so for these 2 points, y2 is 7 minus y1, that's 3, over x2, that's 4, minus x1, so that's minus -2. All right, so 7 minus 3 is 4 over 4 minus -2, that's 4 plus 2 over 6. 4/6, of course, reduces down to 2/3. So now we have our slope, and we have what we need, so we can plug a point and that slope into the equation, and we'll have the point slope form for the equation of the line. All right, so we'll say y minus y1, that was 3, is equal to the slope that we just found. That's 2/3 times x minus x1, that's x minus -2, right? There's our 2/3. So let's go ahead and simplify that. We then have y minus 3 is equal to 2/3 times x plus 2, all right? So there's our point slope form. If we want, and we probably do, want this in our slope intercept form, so we will solve for y. Let's distribute that 2/3. So we'll have y minus 3 is equal to 2/3 x, and then plus 2 times 2/3, or 4/3. All right, we'll add 3 to both sides. So then we have y equal to 2/3 x plus 4/3 plus 3. Well, to add 3 to 4/3, we need to write 3 as thirds. So we'll multiply 3, which can be written as 3 over 1, times 3 over 3, right? 3 over 3 is just 1, so it doesn't actually change that value, all right? So then we have 4/3 plus 3 times 3 is 9/3, right? So our equation would be y equals 2/3 x plus 13/3. And there's a model that we could use. Okay, vertical and horizontal lines are kind of special. A vertical line has the form x equal a, where a is some constant, and it would also be the x coordinate of any point on the line, right? So for a vertical line, if I were to draw that, let's put it here. There's our x, there's our y. Let's put a vertical line, I don't know, right here. All right. If that vertical line intercepts the y-axis at -2, the equation for that line would be y equals -2. All right. Horizontal lines have the form y equal b, where b is some constant and b is the y-coordinate of any point on that line. So if we draw a horizontal line here, there's an x and a y. Let's put the horizontal line, and we'll put it right here. Okay. And if that horizontal line intersects the look what I did, I wrote these backwards. X goes here and y goes up there. Okay, if that horizontal line intercepts the y-axis at 3, I did this backwards here too. I'm having a little bit of a dyslexic day here. That's x equal 2. And there we go. Now we've got these written the right way. So then the horizontal line intersects the vertical axis at y equal 3. All right, let me say that again. X equals -2 is our vertical line, and y equal 3 is our horizontal line. All right. And you know, on the vertical line up here, we see that that line intersects the x-axis at x equals -2. But note that if I identify any other points on that line, like this point here, we could call that, the coordinates of that point would be -2, 3. Here's another point down here. We'll say the coordinates of that point are -2, -1. Any point on that vertical line is going to have the x-coordinate of -2, right? We don't care what y is, but the x-coordinate will be -2. On this horizontal line up here, it intersects the y-axis at y equal 3, at 3, but any other point on that horizontal line will also have a y-coordinate of 3. This point here has the coordinates 4, 3, right? Maybe this point here has the coordinates -2, 3. Any point on that horizontal line is going to have a y-coordinate of 3. All right, so the slopes of horizontal and vertical lines are interesting, right? If we have a slope of 0, right? What would a slope of 0 mean? Well, if we have, think about our slope formula. It's the difference in the y-coordinates of 2 points on the line over the difference in the x-coordinates of 2 points on the line. All right, so let's see. If the difference in the y-coordinates is 0, it doesn't really matter what the difference in the x-coordinates is, because 0 divided by anything is always going to be 0. All right, so this tells us that when the slope is 0, there's no difference in the y-coordinates of 2 points on that line. So what would that look like? Well, if there's no difference, I'll label these correctly this time. If there's no difference in the y-coordinates, right, that means it's the same distance from the horizontal axis, or it has to be a horizontal line. This one right here, we would say is y equals 2. All right, so when the slope is 0, we know that we have a horizontal line, and for the line that's specified here, there's an x-coordinate of -1, and there's a y-coordinate of 5, right? So if I add some more tick marks here, if I put 5 tick marks there, I could say that this is the line y equal 5. All right. So if I were to write the equation of an undefined slope, well, what does an undefined slope mean? Well, an undefined slope, let's see, how do we get an undefined slope? If we look at the formula for the slope, what happens if there's no difference in the x-coordinates, right? What if we have some numerator, don't care what it is, but there's no difference in the x-coordinates? Well, then we have a fraction where 0 is the denominator. Now, can this ever happen? No, we can never divide by 0. When we have 0 in the denominator, we say it's undefined. Okay, so when we see an undefined slope, that means there are no changes in the x-coordinates, or we have a vertical line, right? So for the point given there, let's see, the x-coordinate is -1. So we would have a vertical line right here at x equals -1. Again, horizontal lines have a slope of 0. Vertical lines have an undefined slope. All right. So parallel and perpendicular lines have a unique relationship between their slopes. Parallel lines look like railroad tracks. Okay, they never intersect. Parallel lines are two lines going on forever and ever, but never intersecting. All right, and parallel lines, if the first line is L1, the second line is L2, parallel lines have the same slope. So we could say for parallel lines, the slope of line 1, or M1, is equal to the slope of line 2, or M2. Now, perpendicular lines do intersect. There's line 1, and here's line 2. Perpendicular lines do intersect, and they intersect at a 90-degree angle, right? The relationship between these slopes is that they're opposite reciprocals, or we could say M1 is equal to -1 over M2. Okay, and as a shortcut, they are opposite, meaning they have opposite signs. One will be positive and one will be negative. Look at the slopes. In line 1, we're sloping upward. In line 2, we're sloping downward, right? So they have opposite signs. So we say they're opposite reciprocals. What are reciprocals? Reciprocals. I always struggle with that spelling, reciprocal. There we go. That's supposed to be a C. Something like that. Opposite reciprocals. A reciprocal is, two numbers are reciprocals if when we multiply them by two, if we multiply them together, they equal 1, right? So 1/2 and 2 are reciprocals because I could write 2 as 2 over 1, and when I multiply them, I get 2 over 2, right? Which of course simplifies to 1. All right, so that's what a reciprocal is. And to find a perpendicular slope, what I would do is change the sign of the value and then flip the fraction. If it isn't a fraction already, make it one, like 2 over 1 is, and flip it. All right, let's look at some examples. Here it says, write the equation of the line through the point with the coordinates of -2 and 3. So -2 is our x-coordinate, 3 is our y-coordinate, and parallel to the given line. All right, well, if it's parallel, it's going to have the same slope. However, I cannot determine what the slope is by just looking at the equation when it's in this form. If I solve for y, however, I will have this in slope-intercept form, and I can easily see that the slope will be the coefficient of the x term. So I might be tempted to say that that slope is 5, but that's not going to be correct when I solve for y. All right, let's do it. Let's solve for y. We'll subtract that 5x from both sides. So then we'll have -2y is equal to -5x plus 8. Right, and then divide everything by -2. So then y will be equal to -5 over -2, or the negatives cancel out. So we'll say it's 5/2 x, and then plus 8 divided by -2, or -4. There. Now that we have this equation written in our slope-intercept form, y equal mx plus b, right, I can see that the slope is 5/2. There's our slope-intercept form. And now that I've written it in that form, I know that the coefficient of the x, or the number in front of the x, is going to be my slope. So if the slope of the given line, call it M1, is 5/2, what does the slope of the parallel line have to be the same. M2 would also be 5/2 of the slope of the second point, or the second line, sorry. All right, so to find that equation, let's use our point slope form. Y minus y1 is equal to m times x minus x1. Okay, we now know the slope is 5/2, and we do know an x and y coordinate of a point on that line. So we'll say y minus, for y1, we use 3, is equal to m, that's 5/2, times x minus x1, which is -2. Okay, simplify that a bit. We have y minus 3 is equal to 5/2 times x plus 2. And then if we want to solve for y, we just go ahead and distribute those at 5/2. So y minus 3 equals 5/2 x plus 2 times 5 divided by 2, which is 10/2. All right, then we'll add the 3 to both sides. So y equals 5/2 x, 10/2, of course, is 5, and then 5 plus 3 is 8. And there's the equation of our parallel line. Okay, to find a perpendicular line through that same point of that same equation, we now know we have to think about the relationship between those slopes. Let's see, we already found that 5x minus 2y equals 8. When we solve for y, is y equal 5/2 x minus 4. So there's our slope intercept form. Did I do that right? Yeah, -4. Okay, so we know that the slope of the given equation is 5/2, or m1. Now, what would be the slope then of the equation we're looking for? Call it our m2. The easiest thing to do, we know it's an opposite reciprocal. If it's an opposite reciprocal, it's going to have the opposite sign. Well, m1 was positive 5/2. So m2, the slope of my perpendicular line, is going to have to be negative. And then the reciprocal of 5/2, we just flip it, right? The reciprocal of 5/2 is 2/5. So there's the slope. Now I can write the equation of my line in point slope form. And we'll have y minus 3 is equal to -2/5 times x minus a -2, or x plus 2. All right, solving for y, we have y minus 3 equals -2/5 x minus 4/5. Add the 3. So y is -2/5 x minus 4/5 plus 3, which we need to convert to fifths. Multiply by 5/5. So then y equals -2/5 x. So we have a -4/5 plus 15/5. So that'll be plus 11/5. And there's the equation for our perpendicular line. All right. So there's one more form that you may see a line in, and that's the general form, ax plus by equals c, where a, b, and c are some constants, right? And here's a very nice summary of all the forms for the equation of lines. You have the general form, you have the point slope form, which we've been using extensively, and then you also have the slope intercept form, which is the most useful form, right? This is could also be called the function form for the equation of a line, or the model form. It's how we generally want to write the equation of a line so that we can use it as a function. Okay, and we have a summary here of our vertical and horizontal lines. X equals some constant for our vertical line. And in this case, on vertical lines, we have an undefined slope because it would be result in a division by 0. And then in a horizontal line, it would be y equal b. And of course, when y equal b, the slope is 0. All right, let's talk for a minute about average rate of change. Average rate of change on a line, right, a linear function, is always going to be constant. It's always going to be constant, but not all functions are linear. In fact, many aren't. If we want to find the average rate of change for a function that is not linear, we would still use the same equation for slope, right? But we would want to use our function form, right? So we could say that the average rate of change over some interval of a function, where a is the smallest value of x and b is the largest value of x, we can think about that as the changes in that function value, or f of x values. And f of x is just function notation for y, right, over the changes in the x values, right? Or we could say that's f of b minus f of a over b minus a. And oftentimes we think about these values of these inputs as x values. So you may also see this as f of x2 minus f of x1 over x2 minus x1. And this is simply the equation for the slope, right? Because f of x2, that's just a function notation for y2. F of x1 is just function notation for y1. So it's the same thing as y2 minus y1 over x2 minus x1, right? Where x1, y1 are the coordinates of one point on this graph, and y1 and y2 are the coordinates of, I'm sorry, x2 and y2 are the coordinates of a second point on this graph. All right, so let's take a look at an example here. Here we have some data that's showing Tesla automotive sales for the first 6 years after 2010. All right, so here we have a bar chart on the left, 2 years after 2010, right, or 2012. Sales were 2.65. 2.65, what's our units here? 2.65 thousands. So it's $2.65 $1,000, all right? Year 3, year 4, year 5, all the way up to year 6, where it's $100,000 in sales, all right? So there's a model that was generated from this data, and the model is up here. You go away. Whoop. The model is sales as a function of t, s of t, right? Where s of t is our vertical, or sometimes we think about that as our y, right? And t is our horizontal, or our input variable. We sometimes think about that as our x, right? The graph of the model for sales is over here on the right. All right, so that's the data. Now let's answer a couple questions about it. Part A says find the average rate of change of S of t between 2s of 2 and 6s of 6. So this is saying, this is like the same thing as having an x1, y1, and an x2, y2. We're just using some different notation here. So the average rate of change then is going to be s of 6 minus s of 2 over 6 minus 2. Now, what was s of 6? Let's see, that was 100,000, I believe. There's 6, it's 100,000. And s of 2 is 2.65, all right? So this is going to be 100,000 minus 2.65 over 6 minus 2, or 99,997.35 over 4. And if we plug that into the calculator, we'll find that that divides out to 24,999.3375. All right. So there's our average rate of change over the interval from 2012 to 2016. And these were in thousands. So it's $24,999.3375 thousand. All right. So to interpret that answer, we might say, on average, between 2012 and 2016. Now it's 2012 and 2016 because look, the data is years after 2010, and 2 years after 2010 was 2012, 6 years after 2010 was 2016. Okay, so on average between 2012 and 2016, Tesla sales, oops, increased because it's positive. Oh, excuse me, increased by, and we could say 24, well, let's do it that way, yeah, 24,999.3375 thousand dollars per year. All right, now part C on this example says, what is the relationship between the slope of the secant line joining those 2 points? And my values aren't quite right. Well, we've changed the values, made them a little bit more accurate here. That's fine. So the secant line between these 2 points, no, I don't like this. We're going to use the same values we were using. Oh, they've changed the scale. That's why. All right. Okay. The numbers are different because they've changed the scale. So what is the relationship between the slope of that secant line joining these points and the answer to part A? All right, so the secant line, yeah, no, we have to use the same data. I'm sorry. Even though this graph changed it, the scale, I'm going to put it back the way it was. This is in thousands. Okay, and years after. So 2 is the S of 2 is, what was that? 2 point, let's go back, come on. It was 2.65. Oops, 2.65, and S of 6 was 100,000. All right. So the slope of the secant line then, if we were, let's put the coordinates of those points in, 6, 100,000, and 2, 2.65. All right. So let's go ahead and calculate then that slope of that secant line. It's going to be S. Sorry, 100,000 minus 2.65 over 6 minus 2, or as we already found, 99,997.35 over 4, which of course was 24,999.3375. The exact same thing. And that's what you should always expect to see with finding the average rate of change. The average rate of change is always going to be the slope of the secant line that connects the 2 points on the graph. All right, let's look at one more example here, and I want to show you how to make a scatter plot in both on the graphing calculator as well as in Excel. All right, so the next slide is the data. Let's look at that data. All right, we have years 1980 through 2024 in the X column, and in the Y column, we have public school enrollment. All right, we have a bar chart of that data shown here. Now, to part A here says create a scatter plot of this data, and then take a look at how that line fits the data. All right, let's do it first in the graphing calculator. Turn it on. And to make a scatter plot of the data, you have to enter the data into your calculator, right? So to enter the data, we're going to click Stat, Edit, that's number 1 there. And we're going to type in L1. We're going to type all the years in for list 1. Over in L2 or list 2, we're going to type the public school enrollment numbers in. Okay, so I've done that already. Once you've typed them in, all right, then we want to go to stat plot. So that's second y equal. And you want to make sure you turn your stat plots on for number 1. Okay, mine are on. If yours is off, you just press enter on that number 1. Make sure you're blinking on the on, right? If you were over here on off, just move it over and press enter, and you're turning that stat plot on. The type of graph that you want is the first one, the scatter plot. Right? By default, your X list will be L1, your Y list will be L2. That's what you want. All right, now before we look at the scatter plot, though, we need to specify a window, a viewing window. So we want to make sure we have a minimum X and a maximum X value that's going to show us all the data. Well, our data goes from 1980 to 2024. So I like to go a little bit below the smallest value and a little bit above the highest value. So I did 1970 to 2030. All right. And then for Ys, that's going to be that public school enrollment. All right. And I like, again, to go a little bit smaller. So I did 41,000 as the Y min and a little bit larger for the maximum. So I did 52,500 for the Y max. I scaled it at 10 just because there's much more difference between those numbers. Now, if I press graph, I can see, oops, got something else in there that I didn't necessarily want. Yours won't look like that. Clear that out. There. Yours will look like this. And there's a scatter plot of that data on the graphing calculator. All right. And it looks fairly linear, doesn't it? Oops. Is it exactly linear, though? Well, probably not. Let's see if we can find the average rate of change of the high school enrollment between 1980 and 2024. All right, well, we could calculate that by hand using that rate of change formula, or let me show you how to do it on the calculator. On the calculator, if I go to stat edit, right, and if I take out all the values except 1980 and 2024, it'll make a line form. It'll tell me what that's going to be. So let's do it. I'm going to clear out everything but the first and the last because 1980 was the first and 2024 was the last. All right, so let's see. I think I can maybe just use the delete key on that. Let's try. Yeah, the delete key will work. I want to keep that first value and keep that last value. I want to do the same thing over here in the years. Keep that first value and keep that last value. So now I effectively only have 2 values in there, right? If I graph it, I'll only see 2 points, but I can find the equation of the line between these 2 points this way. If I say stat calc lin reg for linear regression, enter. All right, X list is L1, Y this is L2, and then I'm going to store the equation for that line in a variable. So I'm going to go vars, that's the VARS key, and I'm going to arrow over and click Y vars. I want it to be on function, and I'll just select Y1. All right, now that's going to store the equation it makes in Y1. So when I press calculate now, it's giving me that equation. The calculator uses A instead of M for slope. So it says y equal ax plus b, but a is the slope. And we can see that that average rate of change there was 237.77, some more. And that initial value was negative 429, 139, and some other data. Now, if I wanted to see that graph of that equation, if I click graph again, now it's going to show me the equation for that line. Okay. All right, so part C says write the equation of the line determined by this rate of change in one of the 2 points. Again, I could do that by hand, or I could just use what is in the calculator here. My equation is stored. There it is. It's y equal 237. I'll just say 0.8. We'll round that x. And then my initial value, or my y-intercept, was, let's arrow over so we can see it's not going to, here we go. My arrowing is moving slowly. Let's try that again. Nope, I went up too far. It was negative. Here, I know it's easier to look at here. Stat, calc, linreg. There it is. Okay. Go down to calculate, and it's also going to tell me what it is. There, negative 429, 139. There's the equation of that line. Okay, now we can do the same thing in Excel, and Excel is a little bit prettier and nicer for projects and reports. So let me show you how to do it in Excel. Over here in Excel, the first thing that you want to do is you want to type in the years in one column, and I like to give it a heading, right? So there's the year, type that, and then I went ahead and put the data in a column, and then I did that enrollment. I gave it a title, and I put that in data as well in the second column. All right, then you highlight or select all your data, click Insert from the top, and then we want to go over here. We want to pick, it looks like a little scatter plot here above charts. We want to click that option, and we want to click the scatter option. And now we can see a very nice, I can move it up a little, I can see a very nice graph that's easy, to cut and paste into a report. I can change the titles on that. I can add titles for the axes like that. And I go over there and type in what I want those to be, what I want that to be. I can put, I'm clicking the plus over here. This gives me my options. I call them chart elements. I can put a trend line on there, and it's going to show me the trend line is going to be very similar to the average rate of change line, but it's going to account for all the data points. And let's see, I can see that equation. If I go down here to more options, well, it is linear, but if I go down here to more options, and then where to go? I just clicked something wrong. Trend line options. Let's see. More options. There we go. When you click more options, down here you can say display equation on chart. I click an X, there it is. There's my equation. I might need to move that to see it better. Can't get a hold of it. Anyway, you can move that down, around, if you can get a hold of it. Doesn't want to let me right now. Let's try this. Whoops. I am determined. Well, I can't get my mouse to work properly through this, but you can move that to see that better. But there you see something very similar to what we had. Maybe I can do this. There we go. Got it to move. Y equals 231.52x minus 416,442. Now, it's not the exact equation, right? Because it's taking into account all the data points that are listed there. Right? But it is another way to take a look at a model, or to develop a model, a linear model from some data. All right, that ends the lecture for section 1.4.